Hello viewers, welcome back to the channel DPC Smart. So this is the final lecture on the topic laser under the chapter Optics of MAKAUT BTech Physics syllabus, paper code PH 101 and 201. Here I will discuss about different modes of lasers and also I will discuss about different types of main types of lasers that are within the syllabus of MAKAUT, that is helium-neon laser and RubyLaser. So before starting the video, if you want to join my online classes, then you can contact me through the WhatsApp number and also the Instagram and Facebook given in the background of my screen. And if you like my videos, then kindly like those videos and follow my channel and also subscribe the channel and also share the videos with others. So let us enter the class. Now what are the modes of lasers? Here modes means frequency. The output of the laser consists of number of closely spaced spectral lines and they have different frequencies. Though the desired output should be a single frequency, but due to some losses within the laser we get a spectral band of frequency. That means very closely spaced spectral lines in a broad frequency range, and these losses are due to diffraction, scattering or absorption within the cavity of the resonator, optical resonator. So these spectral lines which are very closely spaced having different frequencies are called modes or laser modes. So these are called laser modes. Now modes are of two types. One is axial or longitudinal mode and second one is called transverse mode. Now what are axial or longitudinal modes? Suppose this one is the optical resonator where the active medium has been placed in between two mirrors, mirror 1 M1 and mirror 2 M2. So mirror 1 has 100% reflectivity and mirror 2 has a 90% of reflectivity. So within the active medium the lasing action will take place. As a result of that, laser radiation or stimulated emitted photons will be created within this active medium. Now those photons or those radiations will be reflected back and forth from this optical resonator, which I have discussed in the optical resonator part in previous lecture. The link have been given in the description section. Now suppose this length of the gain medium be L. So this is the length of the gain medium or the path length of the optical cavity. So now laser radiation will be reflected back and forth from the mirrors M1 and M2. Those radiations will superpose to produce standing waves. So those waves which are reflected back and forth from the mirror M1 and M2, they will produce a standing waves. So the total path covered by those standing waves would be L plus L. So that would be 2L. And we know, as I have discussed previously in my previous initial videos of diffraction, there I have shown how to calculate phase difference from the path difference. If optical path difference is called OPD, then phase difference would be that OPD into 2 pi by lambda, where lambda is the wavelength of that particular radiation or light. So here corresponding to the path difference of 2L, the corresponding phase difference would be d phi, that is 2 pi by lambda into 2L. So this would be our phase difference. Now longitudinal modes in a laser states that only specific frequencies will be present within the optical cavity of laser, and according to the standing wave condition, that phase difference should be integral multiple of 2 pi. That means d phi should be of integral multiple of 2 pi. Suppose that integral multiple is p, then d phi would be p into 2 pi. So this would be the corresponding condition for standing waves. Or we get here lambda equals to, so again d phi I have calculated, or we have calculated as 2 pi L by lambda. So this 2 pi L by lambda, that would be equals to p into 2 pi, or from here we get lambda equals to 2L by p, where L is the path length and p is the integer. So if we get lambda, we can calculate frequency of the laser radiation, that is nu equals to, we know, light velocity in free space c divided by L. So corresponding frequency in air, So corresponding mode or frequency in air would be Cp by 2L, as nu equals to C by lambda. It would be Cp by 2L. The condition is here mu equals to 1, that means when refractive index of the medium is 1, that means in air. So in air medium, the corresponding frequency or mode would be Cp by 2L. So we got nu equals to Cp divided by 2L in when mu 1, that means in air. So now you want to calculate the frequency difference between two consecutive such modes or two consecutive such axial mode when the medium is placed in air. So we have to take here p, one value of integer p and another next consecutive integer as p plus 1. So we have to calculate delta nu, that is equals to nu p plus 1 minus nu p. So if we put the value of p and p plus 1 in this frequency Cp by 2L, we will get delta nu equals to C by 2L. So which is the separation between two adjacent p and p plus 1th axial modes. So separation between two consecutive modes, axial modes, is delta nu equals to C by 2L when we are considering the medium as air. Now in other medium, that means not in air. So for medium other than air, we have to calculate the modes value and distance between two consecutive modes. Now suppose mu be the refractive index of that particular medium. So the velocity of the waves in that medium is given by v mu, which is equals to c by refractive index, where c is the speed of light in free space. So that velocity would be again frequency nu prime mu into lambda. As we know that velocity is frequency into wavelength, so in that medium the velocity would also be equals to frequency in that medium, that is nu mu prime into lambda. Now if we put this value c by mu here, left hand side, we will get c by mu equals to nu m prime into lambda, where nu m prime is the frequency in that medium of refractive index mu. So from here we get frequency, that is nu prime mu equals to c by lambda mu. So from here we get c by lambda mu. Again, according to the condition of modes in axial direction, lambda would be 2L by p. So we put the value of 1 by lambda here or lambda value here, then we get Cp divided by 2 into mu into L. So we get frequency in non-air medium nu prime mu equals to Cp by 2 mu L, that means c into speed of light in free space into integer divided by 2 into refractive index into length of the axis of optical resonator. So this frequency got for mu not equal to 1. Now here also we can calculate the consecutive distance between two consecutive such modes. So mu prime nu p plus 1 and p plus 1th frequency minus pth frequency, that you will get c divided by 2 mu L. If you put p value here and p plus 1 value here, we will get difference delta nu in case of non-air medium, c divided by 2 mu L. So this is how we get the different modes in axial or longitudinal mode, and also we get the difference between two consecutive frequencies. So this one is the graph for axial mode, different axial modes. Here you can see that all these are different modes. This one is the principal mode, and these are the adjacent modes, and these are the differences between two successive modes. So this one is the different spectral lines, these are different spectral lines in laser longitudinal modes, and this difference is the distance between two such consecutive modes. So this is the irradiance versus frequency graph for axial modes. So second type of modes are called transverse modes. So unlike plane wave propagation within the optical cavity or along the axial or longitudinal direction of the optical cavity, there are some other modes also traveling within the cavity, which are out of the axis. That means they are not along the axis of the optical resonator, they are out of the axis, and those modes are not repeated, or they are not able to repeat their own path like axial modes. So here in case of transverse mode, the path length of the modes cannot be repeated or are not repeated. So these wave creates transverse electromagnetic modes or TEM modes. So they are denoted as TEM suffix PQ, where P are the number of minima along horizontal axis or horizontal direction in the laser beam pattern, and Q are the number of minima along the vertical direction in the laser beam pattern. So একটা laser beam pattern এর horizontal direction এ কতগুলো number of minima আছে, that denoted by P, and similarly vertical direction এ কতগুলো number of minima আছে, that is denoted by Q. So this is together TEM PQ. Now if you see this figure, if P value is 0 and Q value is also 0, then the term would be TEM, or transverse electromagnetic wave can be denoted as TEM suffix 00. That means there are no such minima along horizontal direction as well as in vertical direction. So that means there is no minima in the beam pattern of the laser. That means it would be a uniphase mode. So a bright spot would be there. So this one denotes the T00, TEM00. That means transverse electromagnetic mode denoted by TEM00. Now second figure you can see that here TEM10, that means P value is 1, Q value is 0 here. That means along horizontal direction you will get one minima in the laser beam pattern, but along vertical direction there will be no such minima present. So that's why P value is 1, Q value is 0. So it is denoted by TEM10. Similarly, this is TEM20, 30, and this is 01, 02, 03, and etc. So all these are various TEM modes in the laser. So these are the two types of laser modes present within the optical cavity. Now we will discuss about different losses of modes in cavity and a term that is very important for the semester, that is quality factor of laser. Now you have noticed that resonant modes of a laser is not a sharp spectral line, but it consists of a broad spectral range which are formed due to the different spectral frequency spread, and these small spectral spread is due to different losses within the optical cavity, and those losses may be diffraction, absorption or scattering, and they are associated with the modes within the laser, and the measure of that losses are done by a term that is called quality factor. The resonant mode of a laser is not a sharp line, but it consists of a large spectral frequency spread, and this spread is due to the several losses related to scattering, absorption, diffraction, etc., and they are associated with the modes in the cavity. So the measure of these losses are expressed in terms of Q, which is the quality factor. Now quality factor is 2 pi into a ratio. The ratio is the maximum energy stored per cycle in that mode divided by energy dissipated per cycle in that mode. That means output by input, and that quality factor is denoted by 2 pi into that ratio. Total কতটা energy or maximum energy per cycle কতটা stored হচ্ছে in that mode divided by total energy কতটা dissipated হচ্ছে in that mode, and which is also equals to omega by delta omega, where delta omega is the line width or the frequency spread. So Q equals to omega divided by delta omega. So main principal frequency, that means angular frequency divided by angular principal frequency divided by angular frequency width or spread. Now to get high value of Q, we need very low frequency spread. That means narrow line width of a particular mode or frequency. So quality factor we will get higher when this line with is minimum. These are different losses within the mode and quality factor. Next we will discuss one 3-level laser that is within the syllabus of MAKAUT, which is called RubyLaser. Now RubyLaser is a solid state laser, the laser that was first successfully developed by a human being in 1960. First of all, characteristics are it's a 3-level solid state laser, and here ruby is a crystal and single crystal ruby is used, where ruby is a crystalline material, that means alumina Al2O3, in which small amount or small fraction of Al plus 3 ion is replaced by chromium plus 3 ion. That means it is, for its formula would be Al2O3 where is 2 Cr plus 3, where that means Al2O3, some of the alumina Al plus 3 ions are removed and they are replaced by chromium plus 3 ions, and it is a single crystal ruby which is used in RubyLaser, and this ruby crystal is used as gain medium. And here we know that there are 3 components of laser, that is excitation, pump frequency or pump source, one gain medium and optical resonator. Here in case of pumping, optical pumping is used, and 550 nanometer flash lamp or flash tube is used here as an optical pumping, and the output of the laser is obtained 694.3 nanometer and 692.7 nanometer, that means visible red region. So this is the diagram for a ruby laser. Here this one is gain medium. Within an elliptical optical resonator, at one focus the flash tube is placed, and other focus the single ruby crystal is placed. So flash tube emits 550 nanometer wavelength excitation, which is absorbed by the laser, absorbed by the ruby material or ruby crystal, and a output of 694.3 nanometer and 692.7 nanometers are found. So these are the laser output, and this is the different components within that laser, ruby laser. So xenon flash lamp, that means 550 nanometer flash lamp is used as pumping, and this is the ruby cylinder, ruby rod, where this part 2 terminals are optically reflected, is coated with optically reflective medium, where this part is or partly silvered. So laser beam output comes from this part. Now the construction of ruby laser. So ruby laser here also consists of 3 important elements like other laser system, that is laser medium, pump or pumping source, and optical laser medium, the gain medium, the pumping source, and optical resonator. So laser medium or gain medium in ruby laser. As I said, single ruby crystal cylinder is placed on one focus of the optical or elliptical reflector. So 2 planes of ruby cylinders are highly polished. One plane is fully silver coated, 100, that is 100% of reflectivity, and other is half silver, that is 50% silver. Now as very high temperature is produced during the operation of laser, the rod is surrounded by liquid nitrogen to cool the apparatus. Now the pumping source in ruby laser. Here the pump source is the element of a ruby laser system that provides energy to the laser medium. So another focus of the elliptical reflector, a flash lamp tube emitting 550 nanometer light is placed, and which acts as a pumping source. And thirdly, the component is optical resonator. Single crystal cylindrical ruby rod is placed within the optical resonator, where the 2 ends of the rod are flat and parallel, and they are placed between 2 mirrors, and the coating of the mirror is done by silvering, where one end is 100% reflectivity and other end is half silver, that means 50% reflectivity. So the output will come from the as a transmission from the 50% reflectivity end of the single crystal ruby cylinder, and the output would be 692.7 nanometer and 694.3 nanometer. Now working of the RubyLaser. As we know, RubyLaser is a 3-level laser. So it is a 3-level laser system. It is also a solid state laser. Now by optical pumping, that means xenon flash lamp, so electrons from the lower energy level, that is E1, are excited to E3. That is the higher energy level. Now in between E1 and E3, one state, that is E2, is called metastable state, that is formed due to the doping of Cr+3 ions. So this is the energy level of Cr+3, which acts as a metastable state. So E2 is the metastable state. So from E3, so here E1 is the ground level, E3 is the excited level, and E2 is the metastable state level, which has a metastable state has a 10 to the power minus 5 times larger lifetime than the E3 level. So after absorbing the photons, exciting photons, the electrons will reach here. From here they will come to here by non-radiative transition. That means the energy difference would be transferred as a heat. So it will come at metastable state. Now from this metastable state to stimulated emission will occur, and laser emission will take place between E3 and E2. During that process, E2 to E1, the electrons will jump to ground state as a result by the process of spontaneous emission initially. So initially from E2 to E1 there will be spontaneous emission. Due to the spontaneous emission, and one photon will be created. That photon will again dislodge another electron from E2 to reach it E1. So from one photon, two photons are generated. So from one photon to two photons are created, which is called stimulated emission. So laser transition will take place between E2 to E1. So next, another type of laser now I will discuss, that is a gas laser, and the name of the laser is helium-neon laser. So a gas laser is a type of laser in which a mixture of gas is used as an active medium or gain medium. And in most of the practical cases, gas lasers are used maximum. So then in MAKAUT syllabus, the gas laser which is included is helium-neon laser. And now helium-neon laser is a 4-level gas laser system in which a mixture of helium and neon gas is used as gain medium, and the mixture is done such a way that the partial pressure of helium is to neon kept 10:1 ratio. And in case of helium-neon laser, it is the first continuous laser or CW laser that was even constructed first time. Its output of the laser is 632.8 nanometer. So এটা হলো প্রথম continuous wave laser, that means a CW laser that was first made by human being. So similar to the other laser system, it has also 3 components, a pump source. Here electrical pumping is done, that means a high potential difference is applied for electrical discharge. So pumping is electrical here. Second, gain medium. Now the gain medium of the helium-neon laser is made up of mixture of helium and neon gas that I just before few seconds I discussed, that it contained in a glass tube at low pressure. So at low pressure the helium and neon mixture is placed, and the partial pressure is maintained as helium is to neon as 10:1. Third, resonant cavity. Now the glass tube containing this mixture of helium and neon gas is placed within an optical cavity. So thus construction of laser is done. So this is the diagram for the helium-neon laser construction. So this one is the tube, and within this tube helium and neon gas mixture is placed, and a high voltage is applied, about 10 kilovolt. It is applied within this chamber to produce electrical discharge, and which is used as pumping. Now working of helium-neon laser. When the power is on, a high voltage of 10 kilovolt is applied within the gas mixture. Now this power is enough to excite the electrons in the gas mixture. So electrons are produced by the process of electrical discharge within that tube, and they are accelerated between cathodes and anodes. Now the electrons collide with the helium atoms to excite the helium atoms to the excited level F2 and F3. So from ground state of helium atoms, the electrons collide with the helium atoms and make them excited helium atoms, and they reach the excited level of helium atom, which is F2 and F3 in the energy diagram. So this process. So this is the first ground level of helium. This one are the F2 and F3 are the excited level of helium excited atoms, which we denote as He star. Now the excited helium atoms transfer its internal energy to the neon atoms by the process of resonant energy transfer, and it happens with the process of collision between helium atoms and neon atoms. So due to the collision of helium atoms, excited helium atoms with the neon atoms, so an internal energy transfer occurs from helium to neon atoms, which is called resonant energy transfer. So this resonant energy transfer occurs from F3 and F2 level to E6 and E4 level of neon. This is done by resonant energy transfer process, and it happens because F3 and F2 levels are almost equivalent to the energy levels of E6 and E4. Now from E6 to E3 means E6 to E3 excited neon atoms transition occurs between E6 to E3, and which is emitted as laser radiation of wavelength 632.8 nanometer. So here E6 acts as metastable state, and it emits stimulated emitted photons from E6 to E3. After that, from E3 to E2 spontaneous emission occurs. So photons will come, or photons will be created by the process of spontaneous emission from E3 to E2, then it would be de-excited to E2. Then after that, a non-radiative process, the atoms will reach the ground level E1, which is this one is a non-radiative process, and this transition from E3 to E2 is spontaneous emission process. A stimulated emitted photons produced between E6 and E3 will be reflected back and forth by the mirrors of the tube until they are stimulated and produce light amplification. Now apart from the main emission of 632.8 nanometer, other two emissions are also found, which are 3.39 micrometer, which are found from E6 to E5. So from E6 to E5 one radiation is found, that is having wavelength of 3.39 micrometer, and also from E4 to E3 one another extra radiation is found, which is around 1.15 micrometer. So E4 through to E3, that we got 1.15 micrometer. So these are the additional radiation which are in the infrared region of the spectrum. They are also found. So main radiation is 632.8 nanometer, where that happens between E6 to E3 by the process of stimulated emission, and that we got as a output of the laser, of the helium-neon laser. So these are the mechanisms, working mechanism of helium-neon laser that has been written here, and the energy diagram corresponding to this is this one. So this one is for energy diagram for helium, this one is for neon, and all the other energy levels and the corresponding emissions are dictated here. Now what are the applications of laser? That we will discuss at the end part of this video. Now laser can be applied in different fields. First of all, that is in scientific field. So in spectroscopy, lunar laser ranging, photochemistry, laser cooling and nuclear fission, here all this part, for all the purposes laser are used. Secondly, for defense system in the military, so defensive system, different ammunitions and arms, they are also used for as a laser sight, illuminator, rangefinder and target designator. In all the cases lasers have very important applications. And another important application of laser is in the field of medical science, that is during the eye surgery and cosmetic surgery it is hugely used. And fourthly, for industrial and commercial purposes, suppose for different cutting and welding and marking process, lasers are used, as the laser are highly intense light, so they can be used for cutting, welding or marking. In CD player, DVD player, they are also used. In laser printers in our daily life system, it is used as laser pointers. They are also used photographic and lasers light display. For all the cases, for all the purposes, laser are used. So all these are applications of lasers. So this is the end part of this video. See you in the next video. Till then, bye. And don't forget to subscribe, like and follow my channel and the videos.